I'm really excited to present our work today. This research is self-supervised learning for computer vision domain, and we try to build and make available implementation on two popular machine learning frameworks, including TensorFlow and PyTorch, and we will provide the link and also our project implementation. Our multi-data augmentation for self-supervised learning structure lies entirely in this figure, and I will try to explain how we construct and also build this framework. And what we try to do in this research, try to tackle two main challenges of computer vision. One is a data set. So usually to train the large neural net, we require a large human annotated label data, and which is very expensive to construct the dataset. And we try to tackle this problem by training only just taking the input image without requiring any label including during training. And even if we use label, we're just using very small proportion of label. Second is a data efficiency. With the existing small, medium, or large dataset, we using the multi-data augmentation strategy that allow us to increasing the quantity of the training sample, and also with the multi-data augmentation that creating the diversity of the training set, so that helping the training the neural net that more efficient better on the small or medium side of the data. And finally, this project we aim to help researcher and industry related to computer vision application across different tasks and also domains. So I will explain in technical detail in next few slides. Before we jump into the detail, I would like to introduce a bit about the data augmentation, especially for the data augmentation for computer vision. We try to understand what are the data augmentation techniques about and how it works. Here is an example that in the 3D point cloud structure. This example just helps us to easy to understand the data augmentation. So example, we have the original input signal here, so like the point cloud here. And then after we apply the set of augmentation like flipping, scaling, or adding noise, so we will transform the image into the new transform. The new way of looking at an image, but it's still reserving the semantic information of the original input image at the woman here, so we can see. And I have prepared one more example in the images for easy to see also and also understand. I took one image from the CFAR10 dataset and applied the set of transformation in different data augmentation techniques, and as the result we can see we have an image here, and we apply the add to brightness with a magnitude of -33. We can see the image somehow the color transform a bit different, and if we apply the shear here, we can see a bit geometric will be changed, like the shape of the image and also scaling here. So with this example, we can see with one image, and then we apply set of a lot of different augmentation technique, we can generate the new image. But as the human, when we look at this, we still can see some of semantic information of the truck is still preserved after we apply the set of transformation. So these two examples in the previous slide, we can see the data augmentation in a different technique. So in the computer vision, the data augmentation can be categorized into the server main group. I put it 4 here, but it might have more than 4. And how can we group these techniques into different groups? basically it's based on the their property, transformation property. As example, a fine group, this will impact a lot in the this transform will impact to the image geometric transformation. Like rotation, we rotate the image into certain angle, or scaling, we zoom in or zoom out the image, or shear is especially we distort the shape and also translate. And the same is a group is called color transformation. In this transform, they will impact to the color space of the image, and it's the same concept with all the group 3 and group 4. So we just complete overview the general concept of data augmentation, and there will be various augmentation for different group and different kind of transform. So in the self-supervised learning or supervised learning, we need to construct the augmentation pipeline in order to train the neural net effectively. So in our MA-SSRL is a self-supervised framework. So we will construct a pipeline for self-supervised augmentation for self-supervised framework. So we look back our framework again. So in our framework, we much investigate in this blue dash box here, and it's look a lot of component in here, but actually it break down just 2 steps. One, we can see we have to take an image, and then we apply cropping strategy. And after cropping strategy, we apply augmentation strategy. Especially is a multi-augmentation strategy. I think I will explain one by one. So first is a cropping strategy. In the MA-SSRL framework, we investigate 2 different cropping strategy. One is Inception-style. The second is a random uniform cropping. So what is Inception-style cropping? The Inception-style cropping is include 2 main property. One is the area of crop. The second is aspect ratio of crop. So the area of crop will randomly select the value in the range of 0.08 to 1, but it's with respect to the size of the area of the image. The second property is the aspect ratio of crop. So in this aspect ratio of crop will random select the value in this range. This is a fixed range for different data set. So it's 0.75 to 133. So the advantage of the Inception style crop, you can see the aspect ratio crop will help us cover mainly in the central of the image, and also the proportional crop will always larger than 50% of the context of the image. So, but we can see the limit here. If we have a data set that a lot of object may exist in not only in the central, is somewhere in here or somewhere in the part here. So it seems to be the Inception style crop will leading to inappropriate crop when the main area always just like cover entire in the central of the image. The second cropping strategy in our pipeline is a random uniform crop. So in this strategy, the only one property we need to consider about is a crop ratio. In this case, we dynamically define this min and max value. So we can see the high crop will select the value will select in random uniform with our given min and max. So the width crop will estimate through the high crop, and also with the random value multiplied with the random value in the min and max. So in this case, we can see a random crop will help us dynamically define a crop that might suitable for different data set. So if our data set we have an object that did not distribute always distribute in the central of the image, is somewhere here, so the random uniform crop is a good option for selecting the cropping strategy. And in we train on the ImageNet dataset, and then we perform the evaluation between the random uniform crop with the Inception style crop, along with the multiple augmentation technique here, or multiple augmentation method also, and we can say that. So to do this, we using the random crop and Inception-style crop generate the cropping views, and then we apply after that we apply the different augmentation method. We apply 4 different. One is auto augmentation, fast auto augmentation, and sim clear, color distortion pipeline, and also the random augmentation. So as a result, when we train, we perform the self-supervised pre-train on the ImageNet. We found the random uniform crop seem to be performed much better compared to Inception-style crop in wide range with the combination with the different augmentation technique here. So we just understand and see how we construct the step 1 is applying cropping strategy. So in this case, after cropping, we continue using this crop view, perform the multi-augmentation strategy. So in our multi-augmentation strategy, we're including the random augmentation policy, and I will explain with detail, and also the search augmentation policy. So we deep dive into the detail of these two. One is a random and also the search. So we adopt a various method called one is an auto augmentation and sim clear augmentation. So these two is a search policy augmentation pipeline. So first one, auto augmentation. This method is deployed behind the scene. They deploy the reinforcement learning for searching the optimal set of policy for the image transformation. For the sim-clear augmentation pipeline, which is a human expert engineer design, very verify and combination augmentation technique, especially for self-supervised training. The third one is our random augmentation policy. So in this case, we the strategy based on the setup pre-define of the transform spaces is will have a lot of augmentation transform we define at the early, and then we're using the random to define the set of combination of different transformation, and also the corresponding with this is the magnitude. All is a random define and also random select to generate the sub policy. So here is example, we have an image, and then we generate 2 random crop views, and then 2 random crop view after we apply the multi-augmentation will generate 6 different view that contain a different variant property from 3 different augmentation policy here. And here one of the slide to describe entire the augmentation pipeline of the data flow. So we have a cropping view here, and then we apply the auto augmentation technique. So in each single of the augmentation policy here, we contain a multiple sub policy inside. So we can see first is we'll apply sub policy equalize, and then we will have an order transform of image, and then we continue apply the sub policy 2 and with the solarized magnitude 4, and then we can have the image here at the end after the transform for 2 sub policies. So after we just see how we construct the augmentation pipeline and also cropping pipeline. So now we can dive a bit into the detail how we can construct the optimization objective, and also in this stage we see how we optimize the to train the neural net parameter and update it. So the in our framework MA-SSRL especially is a self-supervised framework based joint embedding architecture. We can see with the 2 different branch here, and each branch will contain the set of the neural net architecture. So in here we have 2 encoder, can be the same or different neural net architecture, and then after that the information output of this neural net architecture will continue processing with the multi-layer perceptron layer here, and then at the end we maximize the sum of the output of the latent representation here. I think I will describe detail in the next slide here. Okay, so now we look into the detail of MA-SSRL pipeline. We formulated into different equation here. So first, the data in here as the images. So we can see x0 to xi is mean the number of the image. It can be a lot, so we can just imagine this is an image in our data set. And then image will continue apply the cropping and then the transformation. So in this case we denote augmentation. So one image will generate two augmented version here. So we can see as augmented 1, augmented 2 here of the same image. And then we apply these two images to the two neural net. One is a neural net f theta here is denoted encoder. So the second is a neural net fc. So fc we can see in the joint embedding architecture, especially in our implementation, the neural net with the fc parameter here, it will update based on the theta parameter, learnable parameter here, by using a moving average here. So we denote it here. And then after we have the output from the neural net, and then we continue apply this output representation to the multi-layer perceptron, and it will continue processing and also help us to produce the last output is the latent representation. It's denoted as ZV1 and ZV2 for two encoder here. And in this case, after the output of MLP, we perform the normalization. We're using L2 norm, and then we compute the cosine similarity of these two latent representation embedding on a vector space. And our objective is just minimize the negative cosine similarity between the two latent embedding vector, and we optimize the neural net with the learnable theta hyperparameter here. So in this slide, we can see entire framework can describe in this. It can be easy to understand. So we have image, apply cropping, and then we can see this is the yellow box here is multi-augmentation box here. We can generate 6 different views, and then we passing these each different we passing 2 at once time, and then we generate the embedding, and then we maximize the similarity of each pair, and then we compute the negative the loss, and then we update the neural net hyperparameter here. So after we perform and in this pre-training stage of the self-supervised, I just explain how we optimize the neural net, and then we need to evaluate the obtained representation in the self-supervised pre-trained state. So to do this, first we benchmark or we evaluate the learned representation in the ImageNet linear evaluation and semi-supervised learning. So what is linear evaluation and semi-supervised learning? Let me explain it. So in a linear evaluation, it means we take the pre-trained encoders, like I just showed in the framework is the encoder. It can be the convolution neural net. It can be transformer or different type of the neural net. So we take the pre-trained encoder, and then we frozen these, and then we just adding the new linear classify, and in this linear classify, the number of neurons will equal to the number of the class of our data set. So in this, we just fine-tune and update this layer and frozen entire encoder here without any update here. And in this, we perform in the ImageNet And on the right figure here, we have the evaluation with the baseline, compare also together with the baseline from the DeepMind. It's called BYOL. And in the figure, we apply x-axis. X-axis will be the pre-training epochs in the self-supervised pre-training. The y-axis will be the top one accuracy of the performance when we take the pre-training and evaluate a linear classifier here. So we can see in our MA-SSRL, with the help of the multi-augmentation pipeline, the method can achieve much better performance at the very early training compared to the baseline. It requires large number of iterations to achieve the same the performance compared to our pipeline here. And second, we evaluate on the semi-supervised learning. In this case, we will update encoder, but with very small proportion of label. So in this case, if our data set we have like just small amount of label data, so in this case we can apply the semi-supervised learning pipeline. What we do is we take encoder again, but in this case now we unfreezing the encoder and we update with the label. So in this case, very small proportion of label we update here. And we show the result on the right two figure here is the top 1 and also a top 5 accuracy, and x-axis will represent for the number of fine-tuned epochs on the label data we have here, and the y-axis will show the performance of the top 1 of the accuracy. So in this case we have top 1 accuracy and top 5 accuracy, and we also compare with the baseline BYOL from a DeepMind, and we evaluate on the test set of the ImageNet. So we can see our method has much significant perform compared to the baseline with the fine-tuning pipeline. And also we fine-tune with 10% label, the same setup with the 1%, but in this case we use 10% of label data to fine-tune the encoder. And also our method that can achieve significant better compared to the baseline result. So in this slide, we not only compare to one baseline BYOL from a DeepMind, we compare with the several study, especially MOCO V2 and BYOL from Facebook and one SimClear from Google. So we can see as our method, we only need 300 epochs is equivalent to 1/3 of iteration compared to all these baseline is like 1,000 iteration, but we can achieve state-of-the-art in the semi-supervised evaluation in the ImageNet here. So we can see with leveraging the pipeline of the multi-augmentation, we can achieve much better performance compared to the baseline method. And we continue to take the train or the obtain our representation in the self-supervised stage, pre-trained state, and then we transfer to the multiple distribution natural image datasets. So we perform the linear classification here. So and also we benchmark with the BYOL, and we can see in this we have multiple figure here. So each figure represents for one data set. So here we perform in CIFA 10, Food 101, DTD, and BEST, and Sun 397, and CAR. So this data set is their image distribution is different and variant in different data set. So we perform the linear, it means we frozen the encoder and only just fine-tune the linear classify, and we can see our method perform compare with the BYOL is all in different dataset. We have a significant performance compared to the baseline. And here is a table. We listed all results, and also our method pre-trained only with 300 epochs. We can significant perform compared to the method pre-trained with the 100 epochs, 1000 epochs as a baseline. And here is all of our method described in our we construct the MA-SSRL. So I'm happy to take any question or discussion. So if you can ask in person, please feel free to connect me through email, and I will try to answer all these questions. And thank you so much.